Welcome back to Physical Chemistry on Catalyst University. My name is Kevin Tokoph. Please make sure to like this video and subscribe to my channel for future videos and notifications. In this video and a couple after it, we're going to be doing example problems using one of our real gas equations of state, and that is the hard sphere or hard shell model. Again, one of the models that we can use to predict real gas behavior. Now first let's look at the problem. Carbon dioxide gas, 1 mole of it, at 373 Kelvin occupies 536 milliliters. What is the calculated value of the pressure using the following gas models? We're first going to use the ideal gas equation, which again is something we should be able to use since general chemistry. And then we're going to do the same calculation but with the hard shell equation. All right? And then we're going to compare the two results and draw some conclusions, really one major conclusion. All right, so for the ideal gas equation of state, we know that the pressure is equal to nRT over V. Now, in this case, we're given all of these variables that we need. Okay, so this is pretty much just a simple plug and chug problem. N is our number of moles. That's given to us right here in the first one. That's 1.00 moles, okay, multiplied by R, the gas constant. Now, for our gas constant, I'm choosing to use 0.08206 liter atmospheres per mole Kelvin. Now, the reason I choose to use this particular form of the gas constant with these units is because I'm wanting to solve for a pressure. And this gas constant has units of pressure in it, atmospheres. And so that makes it a good choice to use. Now, technically, you could use the 8.314 joules per mole Kelvin, but the problem there is that the joule is an energy unit. And so we're not solving for energy, so you'd have to do other conversions from there, and it just makes it kind of a pain. So we're not going to use that constant, we're going to use this one. And we'll end up seeing that the units cancel correctly. We then multiply by the temperature, 373 Kelvin, and then we divide by the volume, but we need to make sure to do it in the same units, the same volume units that is, that we have in the gas constant. The gas constant here has volume units of liters, so we need to convert this 536 milliliters into liters. We can do that by dividing this number by 1,000, and this will give us a volume of 0.536 liters. And again, we can see the moles will cancel, the Kelvin units will cancel, and then the liters will also cancel, and that will leave us units of atmospheres, which makes sense because we're solving for a pressure. And when we calculate it, we get a pressure of 57.1 atmospheres. Okay? So using the ideal gas equation of state, this is going to be the pressure of this gas. Okay? Now we're going to do the same calculation, but we're going to use the hard shell equation, or the hard shell model. So remember, this equation is a little bit different. The hard shell model pressure is still nRT on the top, but remember we have an effectively reduced volume. Okay, so the denominator in the hard shell model is always going to be smaller because we're subtracting the product of two positive terms, which in all is positive. So the denominator will be less, and that's V minus NB. All right? Remember that NB, that product, is the amount by which the volume is reduced according to this model. Now, we can essentially load up the numerator in the same way that we did the ideal gas equation. We know that we have 1.00 moles of this gas. We have a gas constant 0.08206 liter atmospheres per mole Kelvin. The temperature is the same, 373 Kelvin. And then in the denominator, we're still going to have 536 milliliters, but we're going to have to convert that to liters. So we've got V, 0.536 liters, but now we have to subtract off N times B. Now, N we already know, that's 1.00 moles. What is B? Well, B is a constant that is given for a particular molecule or atom. Okay, these are things you would have to look up in a table, and I mentioned that in the previous video. And typically this A and the B, now we're not going to use A here, we're only going to use the B, but A and B are what are called van der Waals constants, even though this is the hard shell model. The reason for that is the van der Waals equation of state, which we're going to cover next, is actually this same equation, but there's another term added on, or rather subtracted off. Okay, and so we're going to use the B constant. This is one of the van der Waals constant that's still applicable here. And our B is equal to 0.0428 liters per mole. So I'm just going to plug that in down here for B, 0.0428 liters per mole. And if we were to take this quotient, we would find that the pressure according to the hard shell model is 62.1 atmospheres. And you might ask yourself, is this just a coincidence? Is this maybe the case in 50% of the cases, and the other 50% the ideal pressure is greater? And the answer is no. The hard shell model pressure is always going to be greater than that calculated with the ideal gas equation. Okay? And the reason for that is because n is always positive in the denominator here, b is always a positive number, and so if you take a finite volume and subtract off a positive number, v minus nb is always going to be less than just simple v. And so anytime you divide by a smaller number, the resulting quotient is larger. Okay? And so that's one important thing to recognize. The hard shell model pressure for any problem you do is always going to be greater than the pressure if it was calculated using the ideal gas equation of state. Okay? And this also makes sense from a conceptual point of view because in the hard shell model, we take into account only repulsions. And so if we have no repulsions in the ideal gas equation of state, there's nothing like that here, but then we actually have repulsions in the hard shell model. Repulsions tend to increase the pressure of a gas. So if we have repulsions relative to no repulsions, then that makes sense as to why the hard shell model gives us a higher pressure. Okay? Now, it's very important to be able to do this calculation because we're now going to, after we do the next few examples, we're going to move into van der Waals gases using the van der Waals equation of state. And what we're going to find is that the van der Waals equation is essentially this same term right here, nRT over V minus NB, but then we have to subtract off a second term that is actually A n squared over V squared. And so you do need to be able to do this calculation, and then we're going to add something onto it, or subtract off rather, when we cover that equation. All right? So hopefully this video made sense to you. Please make sure to like this video and subscribe to my channel for future videos and notifications. In the next video, we're going to do another example problem using the hard shell model. So join us then. Thank you.